This is a photo just transmitted back by the Hubble Space Telescope, and scientists fell into collective silence after viewing it. This single image hides 200 million stars, each dozens of times larger than the Sun, and they all hail from the Andromeda Galaxy, 2.5 million light-years away from us. What's even more terrifying is that this galaxy is rushing toward Earth at a speed of 110 kilometers per second. In 4 billion years, it will collide head-on with the Milky Way. But you would never guess that the Andromeda Galaxy was actually wounded long ago. Scientists discovered 2 enormous dust rings on it, just like ripples in a pond, suggesting it was once severely impacted. Who was the culprit? It's actually the dwarf galaxy M32, which is still hanging nearby. That devastating collision 200 million years ago almost ripped Andromeda in half. And even earlier, a massive galaxy, M32P, equivalent to 25 billion suns in mass, was directly swallowed by the Andromeda Galaxy, accounting for 1/5 of its current stars. How many neighbors has this violent galactic beast consumed? When it slams into us, will the Milky Way have a chance to survive? Humanity's history of observing the Andromeda Galaxy spans thousands of years. In 964 AD, the Persian astronomer Abd al-Rahman al-Sufi first discovered it, describing it at the time as a faint, fuzzy nebula. It wasn't until nearly 700 years later, on December 15, 1612, when Simon Marius became the first person to observe it through a telescope, that we truly saw its appearance. As time progressed, more details of this fuzzy nebula gradually emerged. In 1764, Charles Messier officially named it M31. But the most significant breakthrough occurred a century later, with the 3rd Earl of Ross, William Parsons, an enthusiastic but eccentric amateur astronomer, who built the massive 72-inch Leviathan of Parsonstown Telescope in the garden of Bear Castle. For 70 years, it remained the world's largest telescope, a unique existence. Parsons used this giant telescope to observe the spiral structure of the M51 Nebula, which we know today as the Whirlpool Galaxy. This was the first time humans had discovered a spiral structure in a nebula. This major discovery instantly ignited the passion for exploration among astronomers. Subsequently, in 1888, British amateur astronomer Isaac Roberts captured the first ever photograph of the Andromeda Galaxy, clearly revealing its iconic spiral structure. Even with photographic evidence, scientists still couldn't determine exactly what Andromeda was. They classified it with thousands of other spiral nebulae. These nebulae shared one common trait. Their motion was distinctly different from the other stars in the night sky. This sparked a fierce debate among astronomers at the end of the 19th century. Were spiral nebulae part of the Milky Way, or were they independent universes, similar to the Milky Way? In 1925, Edwin Hubble successfully solved this mystery. Hubble discovered 2 Cepheid variable stars, known as standard candles, within the Andromeda Nebula. The period and luminosity of these stars are clearly correlated, which can be used to measure the distance between star systems. Calculations showed that these 2 variables were about 1 million light-years from Earth, far exceeding the then estimated boundary of the Milky Way, which was thought to be no more than 300,000 light-years. With this major finding, Hubble proved that the Andromeda Nebula was an independent galaxy. A corner of the vast universe's mysterious veil was lifted. Our universe, right next door, the Andromeda Galaxy, was officially confirmed. It could be argued that the Andromeda Galaxy helps us understand how galaxies operate even better than the Milky Way does. Studying the structure of the Milky Way is extremely challenging because we are inside it, and various factors interfere with observations. Interstellar dust scatters light, making celestial bodies appear redder than they actually are. Precise distance measurement is highly difficult, and foreground noise obscures key details. The Andromeda Galaxy M31 faces almost none of these issues. At about 2.5 million light-years away, it is an ideal natural laboratory for studying galactic structure and evolution. But fully utilizing this laboratory requires ultra-high-definition observation images. Professional astronomers and amateurs alike have observed the Andromeda Galaxy using ground-based and space telescopes from different angles, resolutions, and wavelengths. But the image released by the Hubble Space Telescope on January 16, 2015, eclipsed all previous observations. After 10 years of continuous observation, Hubble synthesized the largest photo mosaic to date. This image spans over 1,000 orbits, integrates more than 600 individual photographs, and has a total resolution of 2.5 billion pixels, presenting the clearest and most complete full view of the Andromeda Galaxy we have ever seen. Let's admire this masterpiece. The image presents Andromeda from a nearly edge-on perspective, tilted 77 degrees relative to Earth's viewing angle. The right side is the northern region, and the left side is the southern region. Astronomers speculate that the Andromeda Galaxy may contain up to 1 trillion stars, but most are extremely dim, making them undetectable even by a powerful telescope like Hubble. Nevertheless, this image can still resolve 200 million stars, making it the clearest galactic image in the universe to date. Through detailed observation of this nearby neighbor, scientists have been able to uncover more about its history, its differences from the Milky Way, and its future evolution. We know the Andromeda Galaxy is a spiral galaxy with a diameter of about 150,000 light-years, featuring spiral arms extending outwards from the core. Nevertheless, many of its features are unique, and this new image finally helps us begin to understand why. This image, captured in 2015, is an important outcome of the Hubble Andromeda Project, HAP. It allows for high magnification, revealing astonishing details. The Hubble telescope spent over 3 years photographing 1/3 of the stars in the Andromeda Galaxy, covering the disk image across 6 complete spectral bands, from ultraviolet to near-infrared. Observing the outer edge of the image, you can see an elliptical star-forming ring, located about 1 kiloparsec from the galactic core. These nascent stars are bluer, hotter, and more metal-rich, containing chemical elements heavier than helium or hydrogen than other surrounding stars. The higher the magnification of the image, the more stars appear. The sheer number is astounding. Researchers on the Hubble team stated that these stars look like dense grains of sand on a beach, reflecting the high resolution of the image. This star-forming ring has puzzled astronomers, but it's not the only mystery. In 2006, researchers used the infrared array camera on the Spitzer Space Telescope to discover a second dust ring. It is located about 0.5 kiloparsecs from the center of the Andromeda Galaxy, having long been hidden from our view. Initially, scientists thought it was a miniature spiral structure associated with a densely overlapping region of stellar orbits. The existence of 2 rings is no coincidence, but where did they come from? These ring structures are about to reveal the Andromeda Galaxy's violent past. For decades, scientists studied this galaxy, yet there was little evidence that it had undergone a violent collision. But these rings tell a completely different story. As David Block, author of the 2006 study, stated, "These dust rings are like ripples in a pond, and ripples must originate from an impact." Indeed, scientists eventually concluded that these rings are the remnants left behind after Andromeda collided with a satellite galaxy. About 210 million years ago, Andromeda collided with a dwarf galaxy, much like a stone dropping into a calm pond. This impact generated a powerful dust shockwave. The shockwave traveled across the galactic disk, leaving behind the 2 ghostly tracks we can still observe today. Block and his colleagues identified the perpetrator of this impact as the dwarf galaxy Messier 32, M32. Today, M32 appears as a bright, fuzzy nebula, located 5,000 parsecs from the center of Andromeda. By using numerical simulations to recreate the collision process, researchers found that the shockwave generated by a head-on collision initiated by M32 successfully reproduced the ring structure we see today. The obvious hole in the outer ring is a unique feature formed when M32 intersected with the core of Andromeda. The simulation experiments even accurately replicated this detail. Since this discovery in 2006, many believed we understood the severity of the wounds sustained by our galactic neighbor. But thanks to the continuous observations by the Hubble telescope, the Andromeda Galaxy is about to reveal even more unknown secrets. The 2022 image of the Andromeda Galaxy is the result of collaboration between the Hubble telescope and the FAST survey telescope, FAST. This survey is an extension of the original plan, specifically focusing on the southern region of the Andromeda Galaxy. Observations spanned from 2021 to 2022. FAST added observational data for 90 million new stars in this survey. expanding the observation range to cover 2/3 of the galaxy's stellar disk. The reason for conducting this dedicated survey focused on the south is that people gradually realized that the polar regions of the Andromeda Galaxy are distinctly different from other areas. The southern region is more turbulent and unstable than the north, carrying more critical evidence regarding Andromeda's violent history, and large amounts of battle scars still remain. Because the light is too dim, these traces are difficult to discern in Hubble images. However, the giant southern stream, GS, in the southern part of Andromeda is a highly identifiable, massive feature. It extends from the south of the galaxy into the galactic halo, spanning about 150 kiloparsecs. You can imagine it as a stream of debris, created by a galaxy that was gravitationally stripped away by Andromeda. The GS stream belongs to a non-dissipational structure, where the stars are extremely low temperature, contain almost no gaseous components, and their orbits, although governed by gravity, do not radiate heat or collide with other stars in the stream, like a group of marbles rolling along their own independent, frictionless tracks. The giant southern stream, GS, Messier 32, M32, and the inner halo are the three most prominent metal-rich features in the Andromeda Galaxy. Some astronomers believe their consistent metallicity indicates that they are all products of another major collision in Andromeda's history, and this collision was far greater in scale than the one that formed the new rings. And this event involves a familiar protagonist. A 2018 study sought to uncover the truth behind this larger collision, and the results once again focused on Messier 32, M32. More accurately, it pointed to M32's ancestor, M32P. Models show that the most likely victim of the Andromeda Galaxy was the early version of M32, M32P. In its prime, this metal-rich, ancient galaxy had a mass equivalent to 25 billion suns. It merged with the Andromeda Galaxy between 5 billion and 2 billion years ago. Its gas was stripped away by Andromeda's stronger gravity, triggering a burst of star formation, creating approximately 1/5 of Andromeda's total number of stars today. We now have a deeper understanding of this galactic neighbor. More importantly, we can now roughly distinguish which stars belong to Andromeda. The Andromeda Galaxy contains billions of mid-aged stars. For years, astronomers have tried to explain this phenomenon. They originally expected Andromeda's stellar composition to be more like the Milky Way, where old stars gather in the galactic halo and younger stars populate the disk. However, if these mid-aged stars were formed during the merger with the M32P galaxy, then we finally have the answer. This is also the source of Andromeda's second wave of star formation. To gather more supporting evidence, we only need to look at the Hubble telescope's newly captured image of the Messier 32, M32 galaxy. If the above theory holds true, then what we see today is the stripped core of the M32P galaxy. This description is highly consistent with observational results. The center of the Messier 32 galaxy hosts a relatively low-mass black hole, with a mass between 1.8 million and 100 million suns. Astronomers can leverage this data to estimate the size of M32P's central bulge before it merged with Andromeda. Calculations show that M32P's central bulge volume was extremely small. This explains why, during the merger process, it was not completely integrated into Andromeda's center, but instead allowed the stripped core to survive on the galaxy's edge. As mentioned earlier, this is still a theoretical hypothesis, but it seems to answer many questions about Andromeda's turbulent history and tightly links several of its most unique features. But things might be more complicated. The Andromeda Galaxy is surrounded by 36 different dwarf galaxies, any of which could have influenced it. These galaxies may have interacted with it in the past. Thanks to the Hubble telescope, we can now observe this neighbor at ultra-high resolution, enabling us to start tracing the clues of small-scale interactions between it and its satellite galaxies. No one can predict what amazing secrets we will discover next. But it's not just about the past. This spectacular image can also reveal the mysteries of our future. As the two largest gravitationally bound objects in the local group, the Andromeda Galaxy and the Milky Way have always been considered the most likely candidates for collision. According to 2012 estimates, Andromeda is approaching the Milky Way at a speed of 110 kilometers per second, and a collision might occur in about 4 billion years. Of course, this might not be a direct threat humanity has to face, but should the collision truly happen, it's curious to see what kind of transformation these two beloved galaxies will undergo. However, before you start envisioning what the Milky-Andromeda collision will look like, it must be stressed that this is still a highly debated topic. Thanks to the Hubble telescope's new images, we have reason to believe that the Milky Way might luckily survive and avoid complete destruction. In a paper published this year, Till Savalaisel and colleagues from the University of Helsinki optimized the model of the local group using Andromeda Galaxy observations from Hubble. Specifically, the Hubble Spectroscopic Andromeda Project (FAD) survey measured the distances of 55 Cepheid variables within the Andromeda Galaxy. This data, combined with orbital data from other local group galaxies like the Large Magellanic Cloud, suggests that the fate of the Milky Way is far more uncertain than previously thought. The probability of merging with Andromeda within the next few billion years is only 50%. Predicting the evolutionary changes of the Milky Way billions of years from now is never easy, but our ability to clearly observe the current state of the Andromeda Galaxy undoubtedly makes the prediction work relatively easier. The efforts of the FAT and FAST surveys have concluded, but the related scientific work has not stopped there. The image details are rich enough to cover 75 8K ultra-high-definition screens. Scientists continue to unearth the hidden clues and secrets within it. This is merely a microcosm of the endless journey of cosmic exploration. The Hubble telescope may have temporarily shifted its focus to other targets, but in June of this year, the Chandra X-ray Observatory released more related images, showing the supermassive black hole of the Andromeda Galaxy in unprecedented detail. With every observation adding new details, the story of the Andromeda Galaxy will become increasingly complete in the coming years. Currently, this is undoubtedly a story to look forward to. I can't wait to witness the next discoveries made by the Hubble scientists.